Quantum mechanics and the Schrödinger equation can explain the consequences of confinement of particles, namely the discrete nature of energies. However, it has many other consequences in the microscopic world and in principle also in the macroscopic world, although there those consequences are not necessarily apparent. Quantum mechanics defines the internal structure of atomic nuclei and also how these nuclei react with each other. An example of such consequences are the two reactions of calcium-40 with zirconium-90 and zirconium-96, for which I measured with others the fusion yield and also the quasi-elastic scattering yield, that's shown on the left. The two nuclear reactions are very similar. The atomic number of projectile and target nucleus are the same, and the only difference are 6 additional neutrons in the zirconium-96 target nucleus. However, both the fusion yield and also the quasi-elastic backscattering yield are very different when plotted as a function of energy. The heavier target nucleus, zirconium-96, appears to fuse much more readily than its lighter counterpart. This can be understood if the probability density for the last neutron of zirconium-96 is considered as the reaction proceeds. These calculations were carried out by Zagrabeyev and published in 2007. Plots of the probability density are shown on the right. It is apparent that even for larger distances between the two nuclei, the last neutron of zirconium-96 has a finite probability of being located in between the two nuclei or even inside calcium-40. This neutron matter between the two reactants forms a neck that enhances the attractive forces between the two partners. Such an attractive neck of neutron matter is not predicted for the lightest system, calcium-40 zirconium-90, so that in this case more energy is required to initiate the fusion process. The venturing of a particle beyond its classically expected boundary is not limited to nuclear physics, as just illustrated for the neutron in zirconium-96. It happens in many quantum mechanical systems. This is called potential barrier penetration. The Schrödinger equation predicts that this always happens when the potential barrier is not infinite in nature, but has a finite height. Then the wave function can penetrate into this barrier, as shown in the second sketch on the top right. Consequently, the probability density is also finite inside that energy barrier, and there is a certain probability of finding the particle there. If in addition the potential barrier has a finite thickness, the particle can even tunnel through this barrier. That is shown in the sketch on the top right. Tunneling of particles is not at all possible in classical physics. In quantum mechanics, the tunneling probability depends on the height of the barrier and on its thickness. The thinner the barrier and the lower it is, the more likely it is that a particle, such as a neutron or an electron, can penetrate through the barrier and tunnel all the way through. This tunneling effect that is correctly predicted by quantum mechanics explains the radioactive alpha decay, and it is taken advantage of in the modern technique of scanning tunneling microscopy. The sketch at the bottom right illustrates the principle of this technique. In this case, the particles that tunnel are electrons that leave the surface of a sample and tunnel into the tip of the microscope. The tip scans the surface of the sample, and if it is placed right above an atom, the number of tunneling electrons is large, and a large current is created that can be detected and visualized. A scanning tunneling micrograph of graphene is shown on the bottom left. Graphene has a chicken wire hexagonal structure of carbon atoms that can be identified on the image. Each bright spot on the image represents one carbon atom. The tunneling of particles through potential energy barriers is a fascinating feature of nature. A correct and detailed description of the atomic nucleus using the Schrödinger equation and quantum mechanics cannot be performed in one dimension, as explored in a previous presentation. Instead, all three spatial dimensions have to be taken into account. The Coulomb repulsion of the protons has to be considered. Furthermore, the orbital angular momentum of all nucleons and the intrinsic momentum of the nucleons themselves, the so-called spin. One of the first physicists to carry out this complex calculation conclusively was Maria Goeppert-Mayer. She published this work in 1950 and with others received the Nobel Prize for this achievement. In the nuclear shell model, neutrons and protons are considered separately, as it is illustrated at the bottom right. As in a simple one-dimensional calculation, discrete energy levels are predicted for both neutrons and protons. The big difference is the Coulomb barrier, shown on the right, that exists for protons. The Coulomb repulsion also lifts the proton energy levels somewhat with respect to the neutron energy levels. The situation is illustrated schematically for the nucleus carbon-12 with 6 protons and 6 neutrons. Both types of nucleons occupy 3 energy levels each. The question arises why those 6 neutrons do not all occupy the lowest energy level. Indeed, this would be energetically the most favored situation. However, this is not possible because nucleons, both neutrons and protons, are fermion particles. Applying quantum mechanics to many particle systems, it can be shown that fermions, in contrast to bosons, cannot all be on the same energy level because they have to be different in at least one quantum number. Since both neutrons and protons have 2 spin quantum numbers each energy level can be occupied with 2 nucleons each, one with a spin up and the other one with a spin down. This is illustrated in the sketch. This ordering of particles that have spin 1/2 and are fermions is known as the Pauli principle. The predictions of quantum mechanics for the atomic nucleus, as they are represented by the nuclear shell model, are illustrated on this view graph. Considering energy quantization, a consequence of the confinement of the nucleons, and their angular momentum produces a series of energy levels that are labeled 1s, 1p, 1d, 2s, 1f, 2p, and so on, starting with the lowest energy. The interaction of the orbital angular momentum of nucleons with their spin angular momentum causes a further splitting and a reordering of these levels. A number of pronounced energy gaps appear. They can be associated with closed shells filled with 2 nucleons, 8 nucleons, 20 nucleons, 28, 50, 82, and 126 nucleons. The predictions of the nuclear shell models therefore explain the existence of these so-called magic numbers. Neutron and proton configurations that correspond to magic numbers are therefore particularly stable and may be associated with closed shells, therefore the name shell model. Not unlike the arrangement of electrons in an atom, the shells of neutrons and protons surround the center of the nucleus, as illustrated in the top right corner. Among others, it was in particular Maria Goeppert-Mayer who developed the shell model. Despite spending most of her career working in unpaid positions, Maria made huge contributions to both theoretical and chemical physics. Her biggest breakthrough was a mathematical model for the structure of nuclear shells, for which she earned the Nobel Prize. The shell model can thus predict the binding energies of nuclei, which can be compared with experimental measurement. Experimentally, binding energies are determined by comparing the mass of the individual constituents, such as the Z protons and the N neutrons, with the total mass of the nucleus. Practically, atomic masses, capital M, are used. This means instead of the proton mass, the mass of hydrogen has to be considered, which also includes the electron mass. The tiny electron binding energy is typically neglected. Multiplying this difference with 931.5 MeV per atomic mass unit gives the binding energy in MeV. The average binding energy per nucleon, B on A, as shown on the right, can then be plotted as a function of mass number A. The single particle shell model of the nucleus is very good at predicting the relative differences in binding energy between nuclei that have closed shells, such as helium-4 and oxygen-16. It is, however, not very good at predicting the general trend of the binding energies, which increase with increasing mass number A until iron 56, beyond which they decrease again to the very heavy nuclei. This general trend is much better explained using the collective liquid drop model. It is therefore apparent that there is no one unique model of the nucleus, but that our best explanation has to involve both single particle aspects of the nucleus as represented by the shell model, and in addition to that, the collective behavior of all the nucleons, which are best represented by the liquid drop model. This view graph illustrates the concept of the collective liquid drop model of the nucleus. It is inspired by actually water droplets, as shown on the top right. Such droplets are spherical when in equilibrium, but they can also deform and vibrate. Sometimes they split into two parts. The physics of droplets is determined by the interplay of volume forces and surface forces, and this concept is borrowed to explain the nucleus. In the case of the nucleus, 5 important aspects can be distinguished, which are illustrated at the bottom. Rather than looking at the forces themselves, it's convenient to consider the energy associated with those forces. That's illustrated in the diagram on the top left. The diagram shows once more the average binding energy per nucleon as a function of mass number A. However, now the 5 contributions associated with the volume, the surface, the Coulomb repulsion, the neutron-proton asymmetry, and the pairing of nucleons are illustrated. Combining all 5 contributions gives a curve that very closely resembles the measured binding energies of nuclei. It is immediately clear that this concept can only give the general trend of the binding energy, however not the local variation due to shell closure that are explained by the single particle shell model. In the same way as molecules in a water droplet only interact with neighboring molecules, due to the short range of the nuclear strong force, the nucleons, protons and neutrons, only interact with their neighbors. That is illustrated at the bottom in the case of the volume term by the black arrows. The binding energy associated with this nuclear interaction between nucleons therefore depends on the number of nucleons involved, and it is proportional to A. Dividing by A, as in the plot on the top left, B on A as a function of mass number A, thus gives a constant contribution for the volume energy. It has a magnitude of about 14 MeV. H2O molecules at the surface of a water droplet and nucleons at the surface of the nucleus do not have the same opportunity to interact because they are missing neighbors. Therefore, the volume energy term has to be corrected for the surface effect. This is achieved by subtracting a term that is proportional to the surface of the nucleus. In addition, it has to be considered that the protons repel each other over a long distance due to the Coulomb interaction. This also takes away from the volume energy and is corrected by subtracting this Coulomb energy. The fact that energy states of nucleons are quantized appears in the collective model of the nucleus through the asymmetry term and also through the pairing term. If for a certain mass number A, the nucleus would only consist of one type of nucleons, say neutrons, then those neutrons would have to occupy very high energy levels in order to fill the quantum states. It is much favorable to have an equal number of protons and neutrons so that both types of nucleons can occupy low energy levels. In other words, an asymmetry between proton and neutron number is not energetically favored, and this is considered by subtracting an asymmetry energy from the volume energy. Furthermore, due to the fact that both protons and neutrons have either spin plus 1/2 or minus 1/2, it is energetically favorable for nucleons with opposite spins to pair. That is also considered, and together with the other four contributions, then gives the net binding energy that can be compared with experiment. The important aspects of the collective liquid drop model of the nucleus are summarized on this view graph. One observes that the behavior of the nucleons inside the nucleus is somewhat collective and has some similarities with drops of liquids. In particular, the interactions between the particles, the nucleons, is short-ranged and therefore saturated. That means a particular nucleon only attracts its nearest neighbors, but not at all any of the other nucleons in the nucleus. However, now considering neutrons or protons at the surface of the nucleus, this strong interaction is limited because there are neighbors missing. The combined binding energy associated with these two effects is thus equal to a term that represents the volume interaction and that considers the fact that interactions are missing at the surface. So the binding energy B is equal to a constant CV times the mass number, which is proportional to the volume, minus a constant CS times A to the power of 2 on 3, which is proportional to the surface of a particular nucleus with mass number A. The linear proportionality with A and the peculiar proportionality with A to the power of 2 on 3 can be readily explained by considering the imperial radius formula, which is given as 1.2 femtometers times A to the power of 1/3. Using the volume of a sphere and the surface of a sphere, which is 4 on 3 r cubed and 4 pi r squared, one can then relate the volume and the surface of the nucleus to its mass number. As the mass number A of a nucleus increases, also the number of protons increases. Their interaction is long range. Each proton interacts with each other proton in the nucleus. Therefore, the interaction energy goes with proton number z squared, or more precisely z times z minus 1. This is considered in the collective model binding energy equation by subtracting a term that consists of a constant Cc times z times bracket z minus 1 divided by a to the power of 1/3. The a to the power of 1/3 comes about because the Coulomb interaction energy goes with 1 on radius, and the empirical mass formula tells us that the radius is proportional to a to the power of 1/3. The sketch illustrates an extreme case of neutron-proton asymmetry, where many more energy levels are occupied with neutrons than with protons. This is clearly not energetically favorable. That's considered by subtracting a term that consists of a constant C asymmetry times neutron number minus proton number Z squared divided by mass number A. The prediction of the liquid drop model for the net binding energy is shown on the top left. Most nuclei have a binding energy per nucleon of about 8 MeV. For lighter nuclei, this average binding energy increases with a local maximum at iron 56. Beyond that, the binding energy per nucleon decreases. This behavior of the nuclear binding energy has important consequences. For example, it only requires a small activation energy to fission very heavy nuclei like uranium-235 so that energy is released by this fission reaction. This is the reason why nuclear fission is a power source and can be used in nuclear weapons. The heavy nucleus uranium-235 is split into two parts that are lighter, therefore have a higher binding energy per nucleon. The energy difference is released. This does not amount to a lot of energy per nucleus. However, if many of such nuclei are split, the energy can be immense. In contrast, if two light nuclei with relatively low binding energy per nucleon are combined in fusion, then also energy is released, since the B on A increases for the fusion product. The first examples of such fusion reactions with energy release occurred during Bigbang Fusion, when helium-3 was made. The reactions were: a deuteron combines with another deuteron to make helium-3 plus a neutron plus energy, or alternatively, a deuteron, which is a proton and a neutron together, plus another proton combines to form helium-3 plus a gamma photon, HF. Once helium-3 has been formed, it can be combined with another deuteron to produce the alpha particle, helium-4, with two protons and two neutrons, and the additional energy is given away through the kinetic energy of the third proton. Looking at the alpha particle, helium-4, we see that it's doubly magic, and we know from the other type of nuclear models, namely the single particle shell model, that this is a particularly stable configuration. After 20 minutes or so, the average pressure and temperature of the early universe was such that primordial Big Bang nucleosynthesis could not continue, and no further nuclei were produced. However, these days, in our times, and for a long time, the nucleosynthesis has continued in stars, and a prime example of this is the fusion reactions that occur in our Sun. The main reaction there is the so-called proton-proton cycle, which involves the fusion of two protons. In contrast to the reactions that I presented before, this does not proceed via the strong nuclear force, but via the weak interaction. The reaction probability is therefore rather low, and the reaction proceeds rather slowly. This has ensured that the lifetime of stars, and in particular the lifetime of our Sun, is rather long, so that on planets like Earth, biological life could evolve and develop. The two protons combine to form a deuteron, so that one proton converts to a neutron. This is achieved by the emission of a positron, and in order to conserve leptons, a neutrino is emitted as well. Prior to the fusion reaction, the lepton number is 0. Afterwards, the positron contributes a -1 lepton number, and the neutrino contributes a +1 lepton number, again giving a net lepton number of 0. The next step in the proton-proton cycle is the fusion of a proton with an existing deuteron. This proceeds fast via the strong interaction, and helium-3 with two protons and one neutron is formed. The excess energy, the binding energy that is released, is carried away by a gamma photon. This is the same reaction that also occurs in primordial nucleosynthesis in the early minutes of the Big Bang. The proton cycle is then completed through the fusion of helium-3 with another helium-3, again via the strong interaction. This forms the alpha particle plus two protons that can undergo further fusion reactions so that a cyclic situation occurs. In future, the Sun will have exhausted its proton fuel, and astrophysically this has the consequence that it becomes a red giant, increasing in size, which will then include the Earth orbit so that the Earth is consumed. Many such red giant stars already exist, and they contain a lot of alpha particles, a lot of helium-4, which then can combine via the so-called triple alpha reaction, via the Hoyle state, and form carbon-12. This is the only way to heavier elements. Without this state, without this triple alpha reaction, the heavy elements that are necessary to make biology happen would have not been created. In a way, this is a gateway to life. This view graph illustrates the important reactions of the proton-proton cycle. All reactions of the cycle are fusion reactions. The start is the combination of two protons mitigated by the weak interaction, making this a rather slow process and therefore determining the lifetime of the Sun. The fusion reactions that follow are mitigated via the strong nuclear force and proceed very fast, leading to the formation of the very stable nucleus with two protons and two neutrons of helium-4. The binding energy that is released is taken away as kinetic energy of protons via the neutrino or the positron or as gamma ray. Since after the final step two protons are released, the process can commence again. In nucleosynthesis, only the triple alpha process, the fusion of 3 helium nuclei, permits the creation of carbon-12, which is the stepping stone for the formation of all heavier elements. In this process that is illustrated here, 2 helium-4 nuclei briefly combine to form beryllium-8, which is a very unstable nucleus. However, occasionally, very rarely, a third helium-4 nucleus joins. A configuration of 3 alpha particles closely joined is very similar to a so-called resonance, a 0+ state in carbon-12 that is excited. If this happens to decay via gamma emission, then carbon-12 in its ground state is obtained. Since in a red giant star helium-4 nuclei are abundantly available, a fourth helium-4 nucleus might approach and the carbon-12 then becomes oxygen-16. Even heavier nuclei can then be created if carbon-12 fuses with another carbon-12 and oxygen-16 fuses with another oxygen-16 nucleus. Due to the trend of binding energy with mass number, the fusion of heavy nuclei becomes energetically unfavored for nuclei that are more massive than iron 56. The question arises, how are the elements beyond iron 56 produced? The answer to that is that occurs in supernovae and via neutron absorption. At the end of the life of a very heavy star, it collapses and an explosion occurs which dissipates the stellar material in all directions. The energy released in this explosion is immense, and in particular many neutrons are released. These neutrons can then be rapidly absorbed by iron 56, which is illustrated on this view graph, so that a very heavy iron isotope is formed. This may be iron 61. If iron 61 decays via beta- decay, a new element is created, namely nickel 61. Further beta decay with the emission of an electron and an antineutrino creates cobalt 61. Since these processes occur on the timescale of the supernovae very fast, rapidly, this process of massive neutron absorption is called the rapid process. In other astrophysical situations, where there are also many neutrons present, the neutrons may be absorbed more gradually. This is also a possibility of creating heavy elements, and it is known as the slow process. The combination of such processes, in which neutrons are absorbed and very heavy isotopes are created, that then beta decay back to the valley of stability, causes the synthesis of the heavy elements that we know. In contrast to protons, neutrons don't experience the Coulomb force. That means even at very low energies they can be absorbed by a nucleus. Successful absorption of a neutron by a nucleus results in a rearrangement of its nuclear structure. Consequently, binding energy may be released. Initially, the released energy is present as an excitation of the new nucleus, which can cause its nucleons to collectively vibrate and rotate. While in general the collective motion proceeds for a long time and a de-excitation via neutron emission occurs, in some cases, such as uranium-235, the nucleus can fission. It splits into two parts. This is illustrated on this view graph. A slow neutron hits uranium-235 and is absorbed. The combined nucleus, the new nucleus, is now unstable, starts to wobble like a perturbed drop. A point of no return happens, in which the nucleus develops a waste. The nucleus then splits into smaller, stable nuclei of barium and krypton, for example, releasing energy and also typically 2 or 3 neutrons. This fission reaction of uranium-235 is the foundation of nuclear power generation and also the development of nuclear weapons. The reason that such nuclear reactions can be used technologically results from the fact that neutrons are readily absorbed and that the reaction itself creates more neutrons that can be readily absorbed. Such a cyclic process is known as a chain reaction. The term chain reaction may be misleading because a single fission reaction through the release of more neutrons can create an avalanche of many more such fission reactions. In such fission reactions, it is a change of nuclear structure and the release of binding energy that causes the next reaction. So fission reactions are an example where nuclear structure and nuclear reaction physics interplay. Apart from their use in nuclear power reactors, fission reactions occur also in nature, for example in a supernova explosion, although there they are not the dominant process. In some uranium deposits on Earth, it could be shown that at some time in their history, in these deposits, fission reactions occurred. The view graph shows that it is not the fission reaction itself that is problematic in terms of peace and security, but the use of such fission reactions to create avalanches, chain reactions. Controlling devices that are designed to release fission energy in an explosive manner, nuclear bombs, is a great challenge for humanity.